Hi everyone, and well, welcome to see you all, friends, virtually. It's still a bit strange for me, but hi anyway. So, as introduced just then, my name's Ben or Benedict Gaster. I'm also known as Cubrew, and I work at the University of West England. Historically, before that, I've been there about 4 years now. I worked at AMD in the US for a long time, nothing to do with audio, on graphics and the graphics cards. And so I'm very excited about the PlayStation 5, obviously. But that talk has got nothing to do with that. And it's about the idea of what I've been looking at, actually, particularly over in lockdown, during lockdown, because of one thing or another. A lot of the work I do is with physical computing, and that had to be put on hold in the beginning of March. So I've been exploring some ideas about the ability to run code, actually, but in particular focused with audio anywhere. And what I mean by that is the ability to compile once and then run that code in many places such that we get, reasonable performance. Because obviously we can do that with Python and stuff, but you wouldn't necessarily get the guaranteed or real-time performance, which is required for audio. So all the material and everything, I'm not going to skip over this slide, is available online, including the slides, all the source code and everything else for the project is available for people to look over, good and bad, and is on GitHub. And there's a project homepage and stuff and things like that. But I'm just going to give a very quick demo of the sort of thing I'm talking about, not to focus on the kind of DSP side of things and stuff, because there's nothing kind of necessarily original with that at all. I mean, it's not bad, but it's kind of just using standard tools and things, but to give you an idea of how this stuff works and what the kind of goal is. And so for this, I'm using this piece of software called Bespoke, which is developed by this chap called Ryan, and you can find him. It's an excellent little modular kind of synthesizer that you can use to kind of improvise and make stuff. And I use it generally, and I just realized that it was a good tool to kind of develop some of this work with. And if some of you might be familiar with it, otherwise not, it's a great tool to look at and play around with. I really enjoy it. But what I'm going to talk about here is a little demo, which I'm going to give. And actually, I'm going to give a broken demo to start with, just to kind of hone the point of what I'm trying to achieve here. So here, this is Bespoke running. It's just running in debug mode. I'm not going to be showing too much usage. But if I load a pre-configured setup here, you'll see that if this over here is a drum player that is actually set up by and included in Bespoke by Ryan. But down here, we've got this empty module. And in fact, I've got lots of audio anywhere modules that you could load in, but you can see at the moment they're all empty. And the problem is that these are all loaded dynamically, just like you would load a VST plugin or an audio unit plugin. The difference is that these units are only compiled once. So the same audio module would run exactly the same on Windows, Linux, or Mac OS, or any other platform for that reason. There's no reason it couldn't run on Android, and so forth. And so to get that to work, just to demonstrate that, I just run a little Python server. Here's the modules that I've got. You can see that they have the corresponding names, and we can just run a Python server, which is just literally serving up the libraries and everything. And there's nothing fancy about it. I'm not claiming anything novel or anything like that. It's just that it demonstrates the fact that these modules, which were written in this thing called WebAssembly, which I'll talk about in a minute, are completely flexible and can happen things. So here you've got this little 4-track tape recorder that's loaded now, and we can control it and play drum beats and stuff and things. Nothing novel or surprising about that. And then we can load things. So there's a little synthesizer that I like to use, and there's a little reverb. And you can see all of these things with the AAs are being, not only are they loaded dynamically, but they're being completely loaded from the web server, which is serving up this thing called WebAssembly, which I'll talk about in just a second. And as I say, that's portable across, just like something like the Java virtual machine is portable across all different platforms, assuming that you've got a piece of software that can manage and load those things. And I'm always worried about time, so I'm going to flip back to the presentation, and we'll move on. So again, I work at university, not in industry anymore, and so this is an experimental system looking at real-time audio built with WebAssembly. And the name WebAssembly can sometimes be slightly confusing because it doesn't have to be for the web. It is also for the web, but not only. And the first part of this talk, I'm just going to give a kind of an overview about what WebAssembly is for those that don't know. So historically, in the web, we would execute JavaScript. That's the most common thing to execute. And I love JavaScript. I'm not going to critique it or put it down here. It has its benefits, and it's certainly very flexible, and I like coding in it, use it quite a lot. But it does have some weird traits. There's certain things, properties that you might expect to be true that aren't true. And equally, more strangely, is that you can assign, many of you I'm sure know this, but you could start off a variable X with one type, just like you can in Python, and then later on, 1,000 iterations later, sorry, you could get, well, not 1,000, but 800, 900 even, sorry, and assign a string here to that. And then, of course, we can write it out here. So it changes its types. And this is really important. It's very flexible. It's interesting, dynamic typing. But when we think about how to compile JavaScript and how that might work, it has some real issues, right? And so this is a kind of visualization of the V8 engine, which was developed in the late 2000s by Google and others to accelerate and on-optimize JavaScript running in the browser, and made it practical to have the web apps that we have today, right? I mean, the web is an incredible resource for executing programs of huge complexity that we couldn't do before then. But it's quite complex, right? We have to have all of these phases going through. And if any of you know about compilers, you'll know that V8 is a phased-based compiler, has multiple stages, and it optimizes. It does actually generate machine code, but sometimes it has to generate these intermediate steps, bytecode, where it kind of interprets it and executes it. And then if something like the variable changes its type, it has to recompile on the fly. And that can be pretty expensive, particularly when you're thinking about audio and the options. And the V8 compiler has no option but to do that, due to the kind of limitations of the fact that the types can change dynamically. And so it needs to trace them at all times and track them. So that adds additional overhead to something. And so to answer this and address this, Alon Zaki, in 2011, kind of thought about, well, what about if we could compile code, so non-dynamic-based languages such as, Python or JavaScript, but look at other languages like C and C++ in particular is what he was looking at, and could we compile this for the browser? And hopefully many of you will be familiar with a tool that he developed at that time whilst he was at Mozilla. He's at Google now, and called Inscription. It's still widely used today. And it was based on this compiler technology called LLVM that could basically compile down to a known subset called ASM.js of JavaScript. And the key thing about that was that they could make certain assumptions so things wouldn't change. And so then in the browser, they could make optimizations and things like that, which could lead to actually running an extensive number of libraries written in C and C++ can now be compiled to the web and executed as though they're then, just recently I downloaded FFmpeg, for example, and that just runs in the browser. You can use it as a library and translate different audio formats on the fly within the browser at pretty good speeds. Okay, and so in around 2013, 2014, not just Mozilla, but some of the other browser manufacturers, actually all of them, including Apple and Microsoft, got together and thought that maybe they shouldn't stop there. What they should develop is a new virtual machine, something like Java or even the JavaScript and Python. These are virtual machines, and they have, certain properties and guarantees that can run them, which is based on a simple stack-based machine. And so not that dissimilar to a standard instruction set for architectures, that could be a portable compilation target for programming languages such as C++, Rust, and so on. but getting close to native performance, they wanted to be able to get close to native performance. And one of the key goals for that was not to require that the JIT engine would have to trace and track the recompilation, because variables might change and everything and stuff and things. And so it's a much more fixed subset of what possible languages could do. And one of the things they didn't add, at least not in the MVP product that they've got, the minimum viable product that they have currently, is garbage collection, for example. So it's based on a stack-based machine with a simple model of linear memory that you can compile languages like C and C++ to. And this is kind of what it looks like in its textual form. It's not designed to be a textual format. It's designed specifically to be a binary format. And again, that was to address some of the issues that they had with JavaScript, where you have text. You end up with having to minify all of your JavaScript documents, removing all the white space and so forth, so they can be transferred across the internet as quickly as possible. But hopefully, for most of you, if you're programmers, there won't be much surprises here. We can import functions from the external world, just like you can in C and so forth. You can export functions to make them visible to the external world. Ones that aren't exported clearly are static in kind of visibility, the C-like thing. And you can define functions, and you can, it's a stack-based machine, so you can load parameters onto the stack, add them, the result will be put on the stack, and so forth. And this is add and subtract. There's nothing really surprising about it if you're familiar with any kind of machine or low-level instruction sets. And so I don't think they would claim that. One of the most important things that you needed for the web, and it's been one of the designs when you've done things like either audio but also graphics in the web with WebGL, is that everything has to be kind of sandboxed and to guarantee that you won't trample on other parts of the web, can't steal passwords, those sorts of things, and you won't crash the browser. And it still happens today, but not as much. And one of the things that WebAssembly does to guarantee that is it has just a simple linear, you can think of it as an array of bytes as its memory, and indexes into that memory are what you don't have pointers per se, you have an offset into that memory. I mean, clearly pointers are just offsets into more arbitrary memory, but here you're sandboxed within a thing. And that means, of course, that you can do bounds checking very simply using hardware accelerated features and things like that to avoid the overhead of continually checking bounds and things like that. So even though its name is somewhat confusing, WebAssembly, or WASM as it's often shortened to, it's not limited to the browser or to the web by any means. I think it was inspired and it was designed by people, particularly by the browser vendors who are focused on that, but it's not at all limited to it. And in fact, there are a number of projects that allow you to run WASM natively, and they all provide runtimes for doing this. The two popular ones are the WASM time, which is developed by Mozilla and by the WASM working group. WASM is developed by some external companies and is very much focused on productization and doesn't add new features all the time. And these two are kind of earlier ones. Well, this is actually one that initially started off, and then the WASM to C is actually converts a WASM file to what they call a portable C file. So it's still C, so you'd have to recompile it, but it doesn't use any operations that are OS dependent, for example. So that doesn't mean that it's not useful if you want to run it outside the browser to have accessibility and access OS-based features. In particular, there's been the working group, the W3C working group, has been pushing to develop this thing called the WASM system interface, or WASI, which is basically a POSIX-like interface, which is supportable across any platform. Well, the intention is, it's not by any means finished yet, across platforms, different OSs and so on that support the virtual running of WASM files. And so it allows you to have file access, things like that, sockets, all this kind of a stuff that you'd expect from a POSIX-based API. And just to give you a little idea about how that might work, I had another demo. hopefully it'll work, that we can compile. And here we've got a little bit of code up here. It's all in Rust. And so again, even if you're not familiar with Rust, hopefully you can see that it's fairly standard. You know, you can do things like open files, and we can, so this is reading a file, this is outputting a file. And, you know, you can process command line arguments, where you can output to standard error, for a std error, for example, here, and things. So really nothing surprising. And if you're familiar with C or C++, it shouldn't be too difficult to understand how these things work. And we can build it for the reason I use Rust, or one, I'm a big fan of Rust, and I'll talk a little bit about that at the end of the talk. But the other part is that it has built into it, you can download it a WASM or WebAssembly backend, so it can generate WebAssembly natively for you without having to install tools like Inscription or the LLVM compiler tools. And so we could just build that, and then you can run it using this WASM time. I generally use WASM time, and basically this is where the resulting WASM got output. We're going to take a hello.txt file, and we're going to output it. It's just a cat function, right, to temp foo.thing. And if I ran it without any additional information, you'll see that this has failed to work. And even though the error message is not very friendly, what it's actually telling us is that I haven't given the WASM time runtime permission to access different capabilities. And that's an important feature of WASM and also the WASI API, is that it's completely secure. So you have to upgrade the privileges to allow it to access and sandbox it. And it's all sandboxed, right? And so you can get, if we did do that, then you can see that it will run it fine by doing that. And it would put the, if we cat /temp /foo, you'd see that it says hello world. No surprise, nothing innovative, but there are some real advantages of doing that. So for me, this implies that we can compile once and run anywhere. Is a pretty interesting idea, particularly if we could do it at where the performance was close to native. Now, clearly, we're not going to be getting native code speeds, but if we could be within a factor of 2 or 3, then we could really make a big difference. And this is with a technology that's only been implemented and optimized, you know, WASM time and WASM over the last year or so. So we're only just starting out on our adventure, unlike something like the Java runtime, for example, which can't get close to this. And it's been optimized for the last 20, 25 years. Okay, so we're starting at a place which is already way surpassing existing runtimes like Python or Java, and we're only just starting. So I think that's quite an exciting possibility. And just to demonstrate that, the rest of the talk, I'll just kind of go through this idea of, could we have finally found the elusive universal binary? This actually was a talk from Alon Zaki, the guy from Inscription and works at Google now, that gave actually in April of this year, virtually, obviously, and was really great when I discovered this talk. Didn't discover it till June, but because I'd been working on this for a few months, and so I'd highly recommend going and looking at that. I'm not going to talk about it anymore, but he's a much smarter guy than me and has done some really incredible work. So, to be honest, to quote Tiffany Aiken from Terry Pratchett, one of my favorite books, you know, things I'm sure will be different one day, but I'm not, you know, going to tell you that it's all perfect and that you should go off and just develop everything in this. This is just kind of an exploratory place right now. And I think that we are getting close to time where you could develop products with this stuff. But I guess, you know, we're starting small, you know, just like oak trees, as Tiffany Aiken would say. And I've already given you a demo of it in Bespoke working here, but here's a little app that I developed originally over the summer, which is a standalone application that just loads different modules and connects them to different input and output devices. But also equally, this is a Daisy, which I think there's a talk later in the week, but I sponsored talk around, this is by, well, maybe that's actually at the Faust conference, sorry. But Aerosmith developed this really nice microcontroller that is runs around 480 megahertz, so nowhere near the kind of Intel processors I have in my Mac, at least until I get my ARM processors. But it's an embedded bare machine. So if you go to the Rust talk after this, you'll see some stuff like this, I guess. and I'm hoping anyway. And this is the VL Tone, which is a nice little Casio. It was the first ever synth I had as a child in the 1980s. So now you get an idea of how old I am. But what I've done is, you can't see it here, but we've actually, a student of mine hacked this, connected it to this just to use the keyboard, and then we run an emulation of the VL tune running on WASM, running on here. So it runs on all these three different things, one on a microcontroller, one on, and these two's on the desktop computers. Clearly, there's going to be some performance limitations at some point on all these platforms, but for these kind of synths, the VL tune is not a particularly processor heavy one. They run no problem at all. We can run a reverb on here, plus they're all running WebAssembly. So it's quite an interesting multi-platform solution. So how does it work? So basically, we take a DSP description, and in this is going to be in Faust, which I'll talk about a little bit in a minute. Doesn't need to be anything that generates WASM. And for me, I'll talk about how I do that in a second, but basically I take a DSP description, the 4-track tape player that I showed you, that's just written in Rust, and there's no Faust code in between. And we generate WASM once, rather than doing the n times that you would do if you used the standard Faust toolkit, or if you're writing C++, you'd have to compile it for each platform, making sure that you get all the libraries and so forth. And to make this work easily and without portability, I don't use any APIs that aren't written by myself. So there's no WASI code in here. So it's completely portable, because WASI is unlikely to be easily run on something like the Daisy, because you're not going to have access to an OS which would provide POSIX-like functionality. I mean, you could maybe make it work, but I don't see the benefits. And but the nice idea is that we compile once and run many times. Okay. A module itself could be made up of some WASM plus some user interface. For me, I'm using HTML, CSS, and JavaScript, but this is nothing to do with the fact that you can make your interface be running. And itself, another part of this project, which I won't talk about today, is actually making the interface description described in WASM itself. And so rather than using JavaScript, you could use a WASM-based API to execute it just like you would execute something like Lua in a game engine or something like that for interfaces, or JavaScript, of course, that's used widely in like Macs, for example. And that's really just an architecture design decision. So the applications just load a bundle. It just describes, that was the thing that I was showing you earlier on, that's just the web server. Most important thing here is that it contains a link or a URL, a relative URL in this case, but a URL that goes to the WASM file that can be loaded. And it's just the same one for all platforms. Okay, and so what does that mean from a DSP perspective? Well, we take our DSP code, we're going to compile it to Rust, and it is worth mentioning at this time, C, C++ are very well supported for WebAssembly, but they're not potentially as good friends, I can't think of a better word for it, as Rust. And I think that's partly because of the world that WebAssembly lives in are also Rust developers, Mozilla in particular. But also, I think, because of it's developed at the same time, in this new generation of languages. And so Rust is definitely very tooled up for this work. However, please don't go away with thinking that it doesn't work just as well with C and C++, because it does. I just don't do that much. I do a lot more with Rust nowadays. Certainly if I can anyway, I much prefer it. The main thing is that we generate WebAssembly out here. We've got some HTML JS for our UI, but that doesn't really matter. And then here on each of the platforms that we care about, we need to have a runtime. Now, this runtime does have to be compiled clearly for every platform. So Bespoke, I had to compile it for Mac, which was really easy because I'm very familiar with that, and Windows, which was less easy because I'm not very familiar with Windows, but it worked. It took me an hour or so to get it configured. I mean, it's built on top of Juice, and Juice is pretty cool for that. So it took away a lot of the pain that I'd had with my other tools, I must admit. And but clearly, as audio developers, about building applications that are run on different platforms. Hopefully clearly this one, where it's running on a bare metal microprocessor rather than a app processor, as ARM like to call them, introduces some different aspects. For example, we're not going to be running HTML and JS here. I've got a little library that connects to pots and sliders, so physical interfaces, much more limited than what I would do on here, for example, partly just out of resources, but also out of reality that the kind of physical interfaces we can have are much more limited. I mean, there's lots of other stuff, but okay. So the bit that we really care about here is that it loads the WASM, okay? And to handle that, we have an API, and C, WASM really is a C interface. And so if you're familiar with this notion of an hourglass-based API, which I'm really quite into because I came from the kind of GPU side of things, OpenGL and DirectX, the API itself is all described using a C-based API. You know, we don't have to worry about ABI issues, things like that. How you implement that underneath, as the hourglass expands underneath, that's kind of completely up to you. And of course, you can write a wrapper in your favorite language around that, because C is a brilliant interface for writing FFIs, foreign function interfaces. It's funny, you know, over the years how I've kind of said to my students, well, C, I don't like it, but I always seem to come back to it in the end. So it's very convenient and certainly avoids the horrible kind of ABI issues that we get with C++ libraries, for example, which can be quite painful. So hopefully when you see the API, you'll see that it's really not very surprising. And again, you know, it looks pretty much like any other audio-based API you'd see. You know, you've got some initialization where you set the sample rate. You can get the sample rate, you get the number of input and outputs, number of voices, for example, which for some, of course, might be just one, you know, could have polyphony. You can set indices, set parameters, and you can discover parameters, indices. One of the key things here, because this is a C-based API, if you looked back, sorry, I should have said that, here, we don't have pointers, but we do have 64-bit unsigned integers, and so we can return effectively a pointer which points to the handle or the module itself. It's completely an opaque type. We're not returning pointers back across this interface. We're returning opaque types, and so you can't do anything with it other than pass it back into the API on the other side. So, you know, you've got an instance of module. Of course, that means that you can have many instances of a module. You don't just have to have one and handle that. There's, again, no real surprising, you know, note on, note off messages for MIDI or whatever. We can have, there's timing messages, so on and so on. Again, I'm not claiming any novelty here. We can compute some frames, the number of frames that we want, and we can get access to its input and output buffers. So this effectively is returning offsets into the WASM linear memory such that we can access or pipe in input audio and output audio. We can build up audio graphs with it and so forth. And actually, to build up in audio graphs, you can have multiple modules and you can set the inputs and outputs to chain them together to avoid copies. And, you know, with a bit of simple graph coloring, for example, you can optimize the amount of buffers that are shared and those sorts of things. And you can, if you want, this is just one example, you can have an external based API. So you can call functions that are provided by the hosting application. So you could define an API, for example, that describes a graphics API or some audio processing that's done on some other unit. Maybe you're offloading to a GPU, for example, to do some physical modeling, stuff like that. So you could have extensions here, which would have to be implemented in the virtual machine, the audio application itself. And so that wouldn't be portable. You know, you have to do that for each platform, but it's still possible. Okay. So, as I mentioned, the components themselves are just written in Faust, which for people who don't know is a domain-specific, purely functional programming language for implementing signal processing algorithms. I love it, partly because it's just, you know, allows you to really focus on the domain of writing DSP code rather than all the complexities of C++. They have lots of tools for generating different languages, so C++ and things. And I extended it a little bit, but not very much. But I extended it to have explicit notion of voices within the language to handle polyphony and so forth. And I'm not going to go into this itself. These things like the H sliders and things will compile down to those API functions that I talked about for getting and setting parameters. These are just a virtual concept. They're not actually representing a slider. What they're representing is something that is a range between these different, and just sets the frequency and the gain, for example. And just to finish up this talk then, what do I mean by the implementation? So this is what a compilation flow would look like, or at least for audio anyway, but I guess in general. And as I said, it doesn't really need to be, it can be any of these things, or effectively, actually, it can be any programming language that generates WASM. Clearly, if you had garbage collection, things like that, they would complicate it a little bit, but it can still be done. You just have to write the garbage collector, and there are ones out there. For me, most of the focus is here from Faust to Rust, but also from Rust. I mean, I use Faust to Rust because it just takes away a lot of the infrastructure. And to handle that, we have a static memory layout of all the inputs and outputs. These are all generated as we compile the DSP code. I won't go into that, but hopefully it shouldn't be that surprising. There'll be n inputs and n outputs depending on the DSP code you write. And we compile the Faust code down to Rust. And you might ask, why Rust? Why do I go via Rust and not directly to WASM? Well, indeed, Faust does have a WASM backend, and you could use that. I chose not to because I particularly wanted to focus on going via Rust, because Rust has some very, very good auto-vectorization tools, and WASM, or WebAssembly, supports 128-bit SIMD, only 128-bit at the moment, but they are going to add additional lengths too. And of course, as we all know, that can make a massive difference in terms of performance for DSP code. And for me, all of the infrastructure I'd written was all written in Rust, and so it was convenient. But again, you don't have to go via Rust. It's just that's what I did. So I built a new tool, basically extended the Faust compiler to generate the WASM code, or the Rust code, that would then be compiled to WASM, taking a DSP. There's a fork of this compiler on GitHub. Most of the work was done by the Faust team. I just built on their great shoulders to extend it just to generate the code that I needed for this. And so I didn't have to do all the hard work of writing a compiler from scratch, which, as most of us would know, is a huge amount of work. But it's worth noting a couple of things why Rust, in fact, turned out to be really useful for this. And in particular, in this compute function here, we can see that it knows the number of input and output buffers it's getting, and it knows that they're mutable or not mutable in this case. And if we carefully decompose these when we come to accessing them, we can make use of what Rust has, this quite complicated and powerful and difficult to use at times borrow checker, which stops pointer aliasing. In particular, it can make certain guarantees around pointer aliasing, which can be a real bind at times. But also, if you want to generate parallel code, if you want to generate SIMD code, can actually be an incredible benefit. Avoids us having to go in and annotate our code with restrict, for example, as you would have to do in C. In C++, restrict is not actually a valid keyword, but if you could do that. And so, but we do have to slightly generate a couple of little things to make this all work, coming from the C world or C++ world, or any world that we would calling through for that. And this is what happens here. We basically convert the inputs into what Rust called slices, where it knows the size, where it's going to apply bounds checking, for example, which could be very expensive if we're not careful. But as you'll see on this, one of this slide here, that if we're very careful and we don't access our inputs and outputs, in this case just outputs, using array indices, where we'd have to do bounds checking, but instead we generate a iterator. We pair up the iterators here, in this case the two outputs, and if we do that, then we can actually use iterators and the iterator loops that Rust provides to access our outputs. And so it's slightly more complicated to set up, but the guarantees that we have no aliases is throughout this code. There is no way we could have introduced aliases to this code. And so Rust can optimize this loop and SIMDize it. And up here, you can see that I've told it to enable the SIMD. It's an extension at the moment in the Rust compiler. But because of that, we know that, and actually if I looked at the WebAssembly, you'll see that it's scattered with SIMD instructions all over the place for the implementation of these loops. And that's pretty hard to guarantee in languages like C and C++. It's not impossible by any means. You can use pragmatism and restrict for non-trivial loops, at least, But here we don't have any. You can see there's no loop carry dependencies or anything like that. That would make this loop difficult to optimize. And because it's zipped and it's already done the bounds checking up here, it never needs to do the bounds checking in this loop as well. So you don't pay the cost of bounds checking that Rust can introduce if you're not careful. So I've only got a few minutes left, and I just thought I'd finish with a couple of slides on, the real question is this any good in practice? And so I'm not going to give you an extensive, there's a paper that I referenced at the beginning, which has got lots more benchmarks in here and so forth, and I'm still developing those. But just to give you an idea, before we look at the WebAssembly optimizations, I just wanted to show you the difference between the Rust, which was using array accesses here, this one, and this is just doing a simple copy in, copy out, and how many megabytes per second we can get. And you can see that this is Rust, which effectively ends up using bounds checking, which is very costly. But with the optimizations I showed you with the iterators and the zipping the inputs together, then we can actually get slightly better performance than C++ in this example, although I think you should take that with a pinch of salt. These probably vary each time I run them, even though I'm obviously running them to check that they're not warming the caches and everything, but still, they're not that very much different. And I often found that, optimized C++ code, it can run faster than Rust, but not that much, and vice versa in some cases. But by the time we've moved from using iterators away from using the bounds checked arrays, we're 20 times faster. So what does it mean to call native code, into the WASM-based runtime compared to a native call? So just calling an empty function in the C++ world or Rust world compared to calling WASM. And this is in microseconds, okay? So it's very, very fast. You can see that actually on an Intel, this is on an i9 Mac, i9, 2.3 gigahertz, not accelerated or anything, but it's virtually negligible for a native call. But even though it's clearly quite a bit slower, about 6 times slower for the WASM or WASM time runtimes, it's still like 0.6 microseconds. Okay, so it's virtually nothing. And you have to remember, at this point, we're doing validation of all the arguments and validating everything. And so the cost here is the validating of the arguments. Once you've started to get your function actually doing something, you'll amortize that cost very quickly. Potentially, of course, we could, if we didn't want to do the validation, turn that off in the WASM or WASM runtimes. They don't have the ability to do that, but we could easily modify and extend that. I haven't needed to do that, so I don't. And here's a simple sine oscillator, and we can start to see that the WASM runtime, this is still in microseconds, okay? So this is still tiny, and we're running, and it's over block size 0 to 1024. I don't know where it's gone from the slide there, sorry about that. But you can see that the WASM time runtime here is actually doing pretty well. It's slightly decreasing as the block size goes up compared to native Rust code, but not that much. We're still, very low things. The WASM time runtime here is starting to get bad because of it doesn't support SIMD. Well, at least the SIMD I was generating caused it to crash, and so I had to turn that off. And when I did one copy in and out, this is just the final one here, doing a native copy in and copying data into the WASM time and then copying it back out. So it's not managing pinned data or anything. It's literally copying the data in to WASM time and copying it back out again. You can see that we've got an overhead, but we're still down in microseconds, okay? And this is again buffer size of 1024. It's very low. And as I said before, I think we'll see over the coming years, this will get more and more optimized, just like we saw the Sun JIT, for example, for Java, become more and more optimized and being able to handle Java code compared to what it could do originally. We'll see a similar thing for the WASM time and WASM runtimes with the JIT compilers that exist for those. So that's it, really. I just wanted to say that there are some limitations of WebAssembler at the moment. In particular, it doesn't support relocatable code. So that can be quite a bind, particularly if you want to load multiple modules and link them together. You can kind of emulate that, and there's ways of doing it. And that's both a bind, but also a blessing. And I'll finish on the note that it's actually incredibly powerful that because you've got all this code at runtime and you're loading it, if you want to build an audio graph, you can take all that and put it together. You can query how many inputs and outputs everything has. You can do that, and you can generate all the code that does all the plumbing for those completely independent modules and literally generate that on the fly. Now, clearly, you'd have to write code that does that. I have a little loader that does that for simple audio graphs. Well, simple code generation that patches it all together. But you could, over time, generate some very highly optimized code for the audio graph, for example. And I guess for graph-based applications in general, there's a lot of mileage that could be got from this. Okay, some more information about the project site, and I haven't checked the thing, but I'm happy to take questions.
All right. Thank you very much, Benedict, for this very interesting talk. We have a couple of questions. So we have one from Parasha. If you're using WASM targets, what does multi-threading support look like? Does it require that development in other languages is aware of being limited to work as... Hang on. So basically, do you require other languages for that? Or is it aware of being limited to work as job queue style threading?
Yes, so I'm not quite sure what that question is, but I can answer a couple of things about threading. So WASM itself, well, in terms of the MVP product, doesn't support threading internally, but there is an extension to that, and it's coming down the pipeline. So you can get shared memory and things like that, as you'd expect. And so you can have multiple WASM modules running within a shared memory context, each in different threads and so forth. So that's that side of things. And that works really well in WASM time, not so well in WASM so far. But in terms of there is an additional issue, clearly, and it's something that I've come up with, that the WASM, you're going to have to care about not only you have to care about the entry points into the WASM virtual runtime. So WASM time itself, is that thread safe? And there are definitely some potential issues there because of, you could be writing from your GUI thread, for example. This is exactly what happened to me. And you're already inside your audio thread, for example, inside the WASM runtime, and you're trying to map the same memory. It's not thread safe in that sense. So you have to be quite careful with that. And so I managed that by actually having things coming in from the audio thread, like control messages, by basically building up a channel which would then communicate that the audio thread would drain, because otherwise it would crash. So there are definitely some potential issues with thread safety that need to be worked through. Yeah, I hope that answers the question.
All right. Yeah, thanks. And so Ryan is also asking, is all of this work available on your GitHub? I will be excited to see examples of how you write these modules and modifications made to Bespoke to allow it to host them.
Yes, Ryan, it's all available on GitHub. And I've actually made the branch. So I forked Bespoke, obviously, into my GitHub, and I made the branch for Audio Anywhere the default. So if you went there, you could see it straight away in the comments on there. Yeah, it's all in there. And I've got some questions I'd love to discuss with you, particularly about the transport layer and some of the things getting into the WASM that I don't have an answer for yet. So I think it'll be really good to have some time to chat about that. Be great.
All right. Robert is asking, how does WASM communicate with the audio hardware layer? Is it part of the runtime client compiled for the chip, or can you include something like port audio with your WASM application?
So yeah, you could include port audio or something like that. I mean, initially I did it with port audio, but it's such a nightmare to get it to run on Windows and everything. So I gave up and used Juice in the end, which is brilliant for that, I have to say. I'm really impressed. And so it's kind of, I think it's orthogonal. You can definitely tie it in. You could tie it in. You could even have it writing out to the buffers. For me, I keep it's in its own address space, and I have some ways of pinning memory so we avoid the copies, although we're only copying small amounts of data in and out of the audio into the WASM world. But to be honest, if you're only copying 64 bytes in and 64 bytes out, it didn't end up being a bottleneck. So I just left it to copy it in and out at the beginning. Obviously, if you're scaling to many channels, you might, just like you would if you've done any GPU programming, there might become a time where you want to pin and some shared memory between the WASM runtime and the CPU world. You know, the nice thing, of course, is that unlike something like a GPU or even a DSP processor, you're running in the same address space. You just have to manage it by hand. So all of that's doable, and it's that is a kind of low-level implementation detail, which I think would depend on your use case, I think.
All right. We have another question from Will saying Rust and Faust and some C and UI and web technologies is a lot of paradigm switching and tooling. Do you think there is potential for DSP natively in Rust?
Absolutely. Yeah, I don't see any reason why not, just like you could. I mean, you know, the thing that would be best for me would be that someone, you know, a Jules, let's say, spent the time and rewrote Juice in, I know that's not going to happen, but, you know, something like that in Rust, completely doable. And I think there would be advantages and disadvantages. You know, I don't try to argue that Rust is better than C++. It's just different, has different. Sometimes I really love programming in Rust, and sometimes I get really frustrated that I can't just hack away like templates. I miss templates sometimes. I know I shouldn't say that, but I do. And so there's definitely, you could write something like Juice in Rust. I don't think it would be any more of a challenge than it is in C++, but clearly it's not a trivial piece of work. And there has to be a financial motivation, I suppose, in the end to get that kind of quality, you know, because, you know, Juice is a very high standard. And I think that, so definitely you could.
All right. Thank you. Yeah, I think that prospect of having something like that in Rust is, you know, maybe it's going to happen. Who knows? Let's see.
Yeah, I mean, it took a while to happen in C++, right? And it took someone like Jules. So hopefully there'll be someone else like that in the Rust community that might end up doing it, I think, hopefully. Yeah.
Let's hope so.
Yeah.
So Victor is asking you for your repository URL.
Oh, sorry. Let's just go. Can you still see my screen?
No, but you can share. You can just share it again if you like.
Oh, did I stop sharing? Sorry.
I disabled the screen sharing for the Q&A so people can see us better.
Oh yeah, sorry, that was my fault. Oh no, well, GitHub. I mean, basically, anyway, if you search for Gaster on GitHub, so Gaster, that's my username, and it's in my pinned repositories there. You'll see it, if that makes sense.
All right.
There's quite a few. There's about 6 repositories. There's different bits, but hopefully you can put it together. If you have any problems, just email me, and I'm happy to answer questions. He says optimistically now, but yeah.
Oh, right. So someone found it and posted it on the Zoom chat.
Okay, cool.
GitHub.com/bgaster. Yeah.
Yeah, that's right. Yeah.
All right. So James is asking, could you please return to WASM restrictions and how they expedite computing the audio graph? I didn't quite grasp the point you were making.
Well, no, there wasn't that. So I wasn't saying what I was trying to say was that. Well, I think so. We're not WASM restrictions per se, but the way that WASM works, because they're basically isolated modules. I mean, obviously you can link them just like you can any other files. You know, you can think of them just like object files. You know, you can link them together and generate them. But they also, you can query them. As you load them, you can query information about them. You know, you could run, as the runtime itself, it could run the get number of outputs, get number of inputs, and things like that. In fact, I actually do run those as I load it. So they're not, obviously you run them to provide information back to the application, but actually in the runtime, I query those functions to then load 2 modules and pin them together, you know, one to check that the inputs and outputs match, obviously, something like that. But you can actually generate additional WASM code on the fly that plumbs those together. So you don't ever have to call into the WASM runtime call process 1, then call back out again, then call back in and call process 2 by copying the data. You can actually generate the trampoline effectively that handles the bridging of those things. And it would be possible. I haven't done this, but if at the end of the function, you could even patch as you jittered it, the call to the next process function. And so effectively it would be as though you're in them. They'd still be running at buffer with, and you're not patching at sample level, but it'd still be running at buffer, but you wouldn't have any of the kind of in and out that you could do. So I think those kind of optimize, and I've done that works. It wasn't too difficult, generate on the fly, but I think you could extend that to more complicated kind of optimizations. So you could get, have some knowledge of the audio graph that you could optimize as you were loading it. I hope that makes sense.
All right. Thanks. And Ryan is asking, can you expand upon the limitation of the code not being relocatable? If this is a very basic concept, feel free to point me at a Wikipedia article or something.
No, so in a relocatable module, you'd have the ability to have, position independent code. So you'd have a pointer that would, all your indexes into memory would be basically off a base pointer, and so you could load them doing that. And you can do that if I can't remember the parameter to Clang, but it's something like -pic or whatever it is, minus fpic or what it is, and that will generate independent code. You can then create a shared object and you can load that in different places in memory. And you can't do that in WASM at the moment. It doesn't support the base offset idea. And so everything is basically offset from location 0 in the WASM linear memory. And so that means if you've got two modules, they're both expecting to have access to memory 0. And so they just end up overlaying each other. They can't share the memory, and so you have to do some special stuff to make that work. There's work to make that happen, in particular in Clang, which there's been a work to generate some extensions to WASM. But as of last week, it was pretty flaky. And I don't know whether that's their number one motive. They've got a lot of other priorities at the moment. And so I'm hoping it will get fixed. But there are ways around it. As I said, you could generate that on the fly, but it's not trivial.
All right. Thank you. 2 more questions, and then we're going to wrap up.
Yeah.
One from an anonymous attendee. Do you see any blockers to use WASM for a mainstream plugin format?
Well, not having relocatable code could be one. Definitely, I think that's one. I think in the future, absolutely not. I think the MVP product, which they had, which was released, I think in 2018, doesn't have all the features that we'd want for plugin. Like, it doesn't have multi-threading. I mean, multi-threading is supported, but it's not a finished product yet. The WASI stuff I talked about, even though I don't use it, there's a potential that we might want to use it inside a portable format. That's still under development. So I think if you ask me that question in 2 years' time, I think the answer would be definitely no. But I think there probably are still some limitations if you wanted to build a real product, in quotes, on it right now. I mean, people are building real products. I just, I don't know how much extra work they're having to do, if that makes sense.
Yeah. It does. Okay. And then final question is from Jules. Sounds like Soul would surely be a perfect front-end language to generate those WASM modules. And I know Benedict has been very aware of Soul from its early days. Can he comment on why it didn't get a mention here?
Oh, Jules, that's so unfair. It would be brilliant for this. I can't dispute it. I'm more familiar with Faust than Soul, not for any other reason. And, I still keep looking at it, but I haven't looked at it in anger. And so when I started this project, Jules, to be honest, I just wanted to use the thing I was most confident with, not in any reason. I actually think Soul would be excellent for this. If you've got a WASM backend, it'd be great to talk to you about it. But yeah, you're 100% right, and I've got no other thing than I used what I was most familiar with.